In this video, we are discussing Reg and Lasso. So we are having one term which we discussed right now, that is a regularization in machine learning. So what is the regularization? So this is the first advanced tactic for the improving the model performances, and it's considered pretty advanced in many machine learning models, and it is really pretty easy to understand and also to implement. We know that in case of the linear models, the first flaw is that they are prone to be overfit with many input features. Now what is the concept? Concept is that let's consider that we are having say 1000 number of records or rows in a particular data set, and we are having say 100 features. So if we fit a linear regression model with all these 100 features, you can perfectly memorize the training set. Each coefficient would simply memorize one observation. So this model would have perfect accuracy on the training data but perform very poorly on the unseen future data. It hasn't learned the true underlying patterns, and it has only memorized the noise in the training data. So regularization is a technique used to prevent overfitting by artificially penalizing the model coefficients. That means those coefficients which are important, they will be having the higher coefficient values. So those feature attributes which are important having the higher feature coefficient values, and those feature attributes which are less variability or less dependency in the outcome decisive process, so they will be having the coefficient value lesser. And it can also discourage large coefficients by dampening them, and it can also remove features entirely by setting the coefficients to 0. The strength of the penalty is also tunable. So now here in case of Reg, you can find that these coefficient values will be increased or decreased, but in case of Lasso, we'll be finding that some of the feature variables will be having the coefficient value which is almost 0. That means their contribution in the linear model will be considered as nothing. So now let us go for the Reg and Lasso for more discussion. The Reg and Lasso is having the full form, that is a least absolute shrinkage and selection operator. Regression are powerful techniques generally used for creating compact models in presence of a large number of features. Problem with large number of features. What are the problems are there? Enhance the tendency of a model to overfit. As low as 100 variables might cause overfitting, cause computational challenges. This with model systems, and this situation might arise in case of millions or billions of features, and that is the case in case of our Reg. Okay. Both Reg and Lasso try to penalize the beta coefficients so that they can get the important variables, and all in case of Reg and few in case of Lasso. That means here, as I told you earlier also, we shall be penalizing some coefficients against those feature attributes which will be having the less decisive role in the output prediction, and we'll be having more coefficient value for those feature variables which will be more decisive. The major advantage of Reg regression is coefficient shrinkage and reducing the model complexity, because here some of the features values will be having a very low the coefficient values. So now it is majorly used to prevent overfitting but not very useful in reducing the number of features. Along with the shrinking coefficients, Lasso performs feature selection as well. Some of the coefficients become exactly 0, and which it means that the feature is excluded from the model. So it is useful for modeling cases where the number of features are in millions or in more. So let us go for some practical implementation of this Reg and Lasso implementations. In this video, we are discussing the implementation of Reg classifier. So here we have imported the respective modules, the libraries. We have gone for sklearn.linear model import Reg, sklearn.datasets import load Boston. So load Boston, you know that Boston is one housing dataset which is having 506 number of records, that is the rows, and 13 feature attributes are there, and one outcome attribute is there. So now this is the Boston dataset. So now from sklearn.preprocessing import standard scaler. We will be normalizing our data, we will be scaling our data, so we require this standard scaler. Now we shall go for this data loading. So Boston is equal to load Boston. So what is Boston here? Boston is nothing but is becoming a dictionary which is having 4 key values and the respective values are there. So we know that dictionary is nothing but key and value pairs. So 4 keys are there and the respective value sets are there. So one key is our data and another key is our target. So now Boston.data is getting assigned onto the capital X and Boston.target is getting assigned onto the small y. So now if we print X and Y, you are getting this respective outcome. You can find that here we are having these X values and we are having the respective Y values are there. Okay, done, good. So this is the array of list and this is the array 1 and this is also another array because X and Y they are printing as an array. Next, we're just defining one object under this standard scalar class and then scalar.fit transform. There is a standard scalar class object scalar.fit transform X. We are getting this X standard. So now here these X values are very less because they have got scaled here. So now we are also printing the scalar and also printing the X underscore std. So here we are having the scaled data and there is the normalized data against the capital X. Now we are going for one ridge regression creation. So now create ridge regression with an alpha value. The hyperparameter alpha let us control how much we penalize the coefficient. So you know that in case of ridge it is one kind of regularization technique, and in this particular technique what is happening, we are just penalizing or dampening those coefficient values against those future variables which are less decisive in the outcome. So that's why we'll be putting some less coefficient values so that whenever the smaller coefficient values are getting multiplied with the feature variable value, so the contribution will be lesser. So the hyperparameter here it is alpha and let us control how much we penalize the coefficients, and with high values of alpha creating similar modelers, and the ideal value for alpha should be tuned and like any other hyperparameter. In sklearn, the alpha is set using the alpha parameter. So here is the respective parameter alpha which is getting set as 0.5. So we are creating one ridge class object, that is a regr. So that is one regression object. So now using the fit method we are making the model trained. So this particular regression model is getting trained with the X standard, that is a scaled value for X and Y here. So here we are printing this regression object and also the model. So here is a respective outcome. You can find that here the alpha value has been set as 0.5 because I passed that parameters, and rest of the coefficients, rest of the arguments are getting the default argument values. So now we are going for the coefficients. So here we are getting these coefficients. So we are having 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 because 13 feature attributes were there. So 13 coefficients are there. You can find that some of the coefficients values are very less because they have got penalized, they have got dampened. And here we are having the respective model intercept. The model intercept can be obtained using model.intercept underscore. So that is the model intercept because the model has been formed after doing the fitting, after getting the training based on the X standard and the Y values. So here is the respective intercept is there. So in this way we have created one ridge regression. Now we are going for the lasso regression model. So here also we are just importing the lasso, that is a sklearn.linear model import lasso, sklearn.datasets import load Boston, and sklearn.preprocessing import standard scalar. Okay, now in case of lasso, at first we are importing all the required libraries. From sklearn.linear model import lasso, from sklearn.datasets import load Boston, and from sklearn.preprocessing import standard scalar because we are going to normalize or scale our X values. So now at first we are calling this load Boston and it is returning one dictionary. Dictionary is key value pairs as we discussed. So Boston.data is getting assigned onto the X and Boston.target is getting assigned onto the Y. So print X and print Y, you are getting the respective, these arrays are getting printed. Okay. Now we have just defined one object under the standard scalar class, and this scalar.fit transform. So X is getting scaled, X is getting normalized, and the values are getting dumped onto this X underscore std, that is the array variable. So here you can find that we are having the respective contents. Now we are going for the fit ridge regression. So now here we will be going for, I think it is better to make it a lasso. Okay, so where there is a fit lasso regression, the hyperparameter alpha let us control and how we can penalize the coefficients with a higher value of the alpha, creating the simpler models. The ideal value of alpha should be tuned like other hyperparameter. In sklearn, the alpha is set using the alpha parameter. So here is the alpha parameter is there. So we are going for this respective lasso here. So regression is object, so lasso alpha is equal to 0.5. So fit the linear regression. So we are going for this fit. We are using this x standard and the y here. Fit means the learning and the model is getting learned. We are just printing this regression class object and also this model here. You can find that alpha value is set with 0.5. Now we are going to print the model coefficients. It is very important, very interesting to see that we are having 1, 2, 3, 4, 5, 6. So out of 13 feature variable, we're having the 13 coefficients. Out of the 13 coefficients, we're having the 6 coefficients with the coefficient value is equal to 0. And so we are remaining with the 7 of them. So 1, 2, 3, 4, 5, 6, 7. So 7 of them are having the non-zero. So non-zero coefficient value. So those feature variables which will be having the coefficient 0, that means they will have no contribution in the y value decision, y value calculation. But the rest of the 7 feature values are having non-zero coefficients. So they'll be having some contribution in the y value decision process. And also we have printed the respective model intercept. So in our discussion, we have discussed that how this ridge and the lasso regression models can be implemented using Python coding. Thanks for watching this.